Hi guys, I'm Jay. Today, I'm going to talk about Ludwig Prandtl. Hope you guys will enjoy it. So let's have a quick introduction of this great scientist. Ludwig Prandtl was a German aerodynamicist and one of the leading scholars in the development of systematic and mathematical analysis. He was also the first person to introduce the boundary layer concept, which made huge contribution to the development of fluid mechanics by simplifying the equations of fluid flow. Moving on to the boundary layer concept, Ludwig Prandtl suggests that flow field can be divided into two areas, the area outside the boundary layer and the area inside the boundary layer. Fluid flow outside the boundary layer has features of constant velocity and pressure. Also, it is steady, inviscid, and incompressible. While the fluid flow inside the boundary layer has very large velocity gradients, it is also dominated by viscosity and responsible for the large drag on body. In other words, friction caused by fluid flow outside the boundary layer is negligible compared with the flow inside the boundary layer. In the graph, you can clearly see position of the layer, that the thin boundary layer is covering the aerofoil, and flow outside the layer is inviscid. There are two different types of boundary layer flow, laminar and turbulent. For laminar flow, it creates less skin friction drag, is very smooth, though less stable. The thickness of this kind of flow also increases as the flow continues. In the right-hand side, you can see how the boundary layer concept helps simplifying the continuity equation and the Navier-Stokes equations into a much easier parabolic PDE. On the other hand, for turbulent flow, there's no unique Reynolds number that indicates the exact position of the laminar to turbulent transition. However, experiment tells us that it often happens at around 500,000 Reynolds number. This flow contains swirls and eddies, creates much more skin friction drag than laminar flow. More importantly, its equation is far more difficult to solve due to the time-dependent variation of these flow properties. Hence, there is yet to have an universal similarity solution. This is the end of my video. Thank you.